Very good afternoon. So, lecture 17, we'll get into some very serious analysis. For some reason, that didn't show. Still not shown up, right? Okay, while it shows up, the study today will be on serious stochastic approaches, inspired, of course, by accelerated gradient descent and the likes. So, we've already started the stochastic gradient descent and its accelerated versions will be covered today. Then we'll move on to generalized proximal gradient descent and constraint optimization and projected gradient descent. Hopefully, we are able to cover a lot of this by Thursday. So, summary, after we actually included, or rather, we looked at the convergence of subgradient descent vis-a-vis gradient descent, right? And we compared. So if you look at Lipschitz continuous functions case with gradient descent, you got R square B square by epsilon square. And if you look at the subgradient method, we get order 1 upon epsilon square again. Okay. So that was reassuring. The two challenges or two caveats were subgradient requires more assumptions. So here you see there was some bunch of more assumptions on gamma t were required. What was the assumption on gamma t that was required? Anyone can recall? Yes? Huh? Yeah, the summation of the gamma t should be summation of gamma t, or gamma t is should tend to 0. But the summation of the gamma t should be, yeah, infinity, because there was 1 upon summation gamma t term, right? Additionally, summation of gamma t square should also be finite. That covered up all the cases. The other assumption that was required was that subgradient descent is really not subgradient descent. It's a subgradient. Descent may or may not be assured, and therefore we had to look at the best iterate at every step. But good thing that we kind of triangulated for similar kind of results, and then we moved on. We said, well, can we do something more? Subgradient descent, of course, is very much inspired by machine learning. Can there be something more grounded in machine learning? And we said, well, go back to all our favorite loss functions. All of them have a summation with an index on the examples, right? Now, is there something interesting we can do with respect to those example IDs, the I, right? And we go back and look at, say, support vector machines. We find that, well, even with support vector machines, not all points contribute to the separating or supporting hyperplanes, right? It's only some supporting vectors, support vectors, that actually contribute. That inspired us to think of whether we can actually consider only a subset of these indices, right? Which subsets to consider? Of course, then we spent a lot of time discussing, grad match. That was our own work. There are also many other approaches like crust, which does a singularity decomposition of this massive Jacobian to find out which set of points are good. He said, well, all that is great, good inspiration, but let's get started with something very simple, which is just randomly sampling points. A subset selection is certainly of value. Right? Let's start with a random sample. So instead of evaluating the full gradient of the objective, if we only look at the example I randomly sampled to update the parameters W at iteration index T, what happens, right? And then we concluded with, well, if you pick uniformly at random, certainly there's each iteration is going to be n times faster because you are avoiding a summation over all the examples. Is that good enough? Iteration being n times cheaper, but understand that GTI, or which is gradient of FWT with respect to the ith point, is still an approximation to the gradient over all the points. How good is this approximation? That's also important. Just getting speed up without rationalizing the effectiveness is not good enough. Right? So efficiency and effectiveness both are required. So we said, well, towards understanding the effectiveness, what if we look at this inequality, assuming convexity? As I said, convexity is always our medium or tool. So typically when we looked at convexity, we would have f of Wt minus f of W star, right? We would have this to be less than equal to the gradient f at Wt sorry, I meant the other way. Yes, yes, yes. Right. So sorry. So will this inequality hold? Right. That was the question. And our analysis was that, well, if I replace this GT with GTI, which means if I take only the ith example here, everything else remaining the same, right? This inequality should hold if you, so this is the original inequality, right? In case you are wondering where did we get this from, so f of W star is greater than or equal to f of t plus, right? F of this is a lower bound. This approximation, linear approximation f of Wt plus the gradient at point t, W star minus Wt. So this inequality, you just bring the f of W star to the other side and the gradient W star minus Wt to become Wt minus W star. So both sides, the signs, the order changes, and this is how you get the original inequality. Now, if you were to what did I do? Okay, so I didn't change it. This is no. This is correct, right? This one. This one. So this is what we have, right? W star is lower bounded by f of W star is lower bounded by f of Wt plus the linear approximation. No, I'm talking about this one. This one. Wt minus W star here. Here it is W star minus Wt. See, f of W star is greater than or equal to f of Wt plus GT transpose W star minus Wt. You get this. So now work backwards. Right? So then what do you have? If you bring W star to this side, f of W star minus f of Wt, sorry, yeah, f of Wt minus f of W star is less than or equal to, bring this to the other side, GT transpose, this Wt minus W star will become W star minus Wt. Right? So this is fine. So I think that's what I had written earlier. Okay. No problem.
Here, what data?
Loss function is linear, yes. Loss function is linear in the sense that the loss function is evaluated on each data point independently. So if the question is, what happens if I can't sum, right? So what happens the if this doesn't hold, right? The gradient is not a summation of the gradients of individual points, which is true, which is a very, very valid point. This holds when, for example, you have an IID distribution, but often you don't have IID, independent analytically distributed points. You don't have. In fact, if you're looking at something like sequence stacking or classification of images, I mean, you don't have the loss decomposed over each pixel, like we showed here. It's a valid point. And in such cases, well, either you have to do approximation, consider the pseudo likelihood, log likelihood, or bring in some more assumptions, which may not be like IID assumptions, but which let you, instead of writing it this way, right? For example, the sum over gradients, you may have some matrix which is block diagonal, which has some nice structure basically. Here multiple gradients. So would it be better to rather than would it be better to like put the gradient that are not aligned from 0. So this question is, instead of taking independent points, why not consider a gap, a mini batch, right? Some kind of a grouping of points which are. So basically, we are assuming convexity. Right. So the gradient, all should have a different direction, single direction. So the problem with subgradients that it can have a probably direction and different direction. So why don't we, instead of avoiding those points, why don't we use that to just neglect those gradients? Neglect gradients, or ignore points whose gradients are not aligned with the overall direction, right? Like what we consider the momentum approaches. We wanted, I mean, the best result is when the cumulative effect of gradients is in the same direction. So basically, discard points which are not agreeing with the majority direction. See, there is a problem in doing that, right? The majority gradient direction right now at the current iterate could be itself wrong, right? So we want to do course correction. That's why we brought in curvature. That's why we looked at Lipschitz properties to do some course correction. If you just go by the current consensus gradient and ignore points which don't agree, then you possibly are going to get stuck in some local minimum. You may just overfit on a subset of points. So that may not be good enough. Okay. There is a strong convexity assumption here. There's no strong convexity. There's convexity here. This is just the convexity property. Okay. Any other question? Very good question. Yeah. Yes, that's exactly. Yes. Huh. I didn't complete the story. So what I'm trying to say is this is a summation. Okay. So I look at the equation here. So I have Fi Wt minus Fw star less than equal to the overall gradient, which could be also viewed, as you pointed out, as summation over all the gradients of the individual points Fwt of Wt minus W star. Okay, this is fine. The injustice we are doing here is you're saying, well, we'll retain the summation here on the left hand side, but drop the summation on the right hand side. That is the problem, right? So this is all fine. The part in red is all fine. The part in green is where we have a problem, right? No, not really part in green. I mean, this is still true. Part in green is still true. But the problem is if I start dropping the I index in the green part, f of Wt minus f of W star less than equal to Gt I transpose Wt minus W star. That is a problem. You understand? So when I convexity says overall function is convex, and function with respect to all the points is convex. Okay, a function evaluated on a single point is also convex, provided you use a gradient only for that point. But if you start using the function over all the points, but the gradient only at a single point, then you have a problem. Is this clear? No, not here. So this is still okay. This is all still okay. The problem will be next. So far it is all fine. The problem will be now when I start assuming that we have gradient on one point, but the function is on all the points. Okay. So whatever I have written here is all fine. Issue will be when I drop the summation on the right hand side and keep the summation on the left hand side. Okay, so right, so this is what I'm trying to say. If this point is sampled, okay, so if you want, I can make this explicit. This GT transposes GTI. Okay, so we have assumed here assumption is that this GT is a so when we start assuming that the GT is evaluated on a randomly sampled point, then we have a problem. Is this clear? Okay, so hereafter instead of putting I index, we'll just use GT. Okay, so the summation is fine. I'm going to replace this. I'm going to replace the gradient evaluated on the ith point with the current iterate WTS as GT. Because the I is random, right? I mean, how do I even? It's difficult to keep using the word index I because then it look like it's a particular index I. Is this clear now? So this inequality, of course, I mean, if you can, you may use a 1 upon n there, right? So there's a 1 upon n there. We have not used 1 upon n here, but 1 upon n means this. So the question is, how does this compare? So what are we trying to do? Comparing GT, which is the gradient at the ith point, with 1 upon n of the summation of the gradients at the all the n points. This is what we are doing. Comparing GT with the average of the gradients, right? So this inequality will hold in expectation is what where we concluded, right? It will not hold always. It will hold in explanation in expectation if I'm going to replace GT with a randomly sampled point gradient. So this inequality will hold or not hold depending on how stochastic the gradient GT turns out, but it will hold in expectation. That is the key point here. Okay, so GT will avoid using the index I, right? And that's what we did in the previous slide. If GT were to be treated as the a random sample point gradient, then we have a problem with this inequality unless we consider expectation. Okay, so continuing with this notation where GT is for randomly sampled I, right? Continuing with this understanding of GT, it turns out that we can have a similar result as we had for the case of convexity plus Lipschitz continuity. Remember, Lipschitz continuity requires that the norm of the gradient is square of the norm of gradient is less than or equal to b square. The same result holds with an understanding that the expected square norm of the gradient, because now you're sampling a point and computing its gradient, right? So the expectation now will be on the squared norm of the gradient of the point that you have sampled. If that is less than or equal to b square, in expectation, if you have Lipschitz continuity. So earlier we were talking about Lipschitz continuity. Now it's an expected Lipschitz continuity. And we know, if you remember, we had similar step choices. Gamma is r upon b square root t, etc. Right? All this holds. Right? This was motivated from subgradient descent also. But specifically in gradient descent, we found a similar expression r b upon square root t. So in such a case, stochastic gradient descent will give you that the average of the expected error of ft, error in the sense gap, f. So here, please look at it. There's an expectation of fwt minus fw star. Now, if you distribute the expectation, w star has nothing to do with the index t. Therefore, we are considering the expected value of fwt minus fw star. So this summation or average is less than or equal to rb by square root t. Very similar to what we had earlier. So only difference is we have brought in expectations in two places, in Lipschitz continuity and in expectation on the function value. Is this clear? So the analogy continues with expectation. All right. Now you can also consider some slightly different variants. If you consider, for example, differentiable and strongly convex function with parameter mu. Now you'll have to play around a bit with what the step size should be. As I said, some of these are existential proofs, but with some conditions on the step size, like Armio conditions, they generalize as well. Okay, but we don't get into that because it's, as you saw, it's very cumbersome. So we have just considered, okay, for gamma t is 2 upon mu into t plus 1 in the denominator. So basically, it's decreasing with t as t increases. The stochastic gradient descent again gives you something which kind of is reminiscent of what we got earlier. So instead of square root t, now you have 1 upon t. Right? Again, right? Look at this. So strong convexity, gamma t is basically diminishing as t increases. And if you consider the expected value of the function, what are we looking at? We're looking at the weighted average. So function at the average of all the iterates. So this 2 upon t into t plus 1, and there's a summation t. So you can think of, so this is slightly different. Right? So this is not the same expression as earlier. Right? This is more complex because there is a function at, so instead of looking at expected value of the function across all the points, now you have a expected value of function with respect to weighted average of points. Okay. So this can be shown to be having a similar right hand side upper bound. This gap. Okay, so things have started diverging a bit. Okay? At least when you start looking at results on strong convexity. Right, but point is, I mean, this is a little forgivable, right? Basically, if you consider 2 upon t into t plus 1, that is nothing but 1 upon summation t. This entire expression in pink is 1 upon summation over t. And what you're trying to do here is t into wt. summation divided by summation t. So in some expected sense of the weighted function evaluated at the weighted combination of points, we are able to show similar results. Okay. As the strong convexity plus Lipschitz continuity, right hand side is the same. So what is our readout from here? I mean, we see that, well, things are slightly different, but there's a similar flavor in the sense of stochasticity. And now a little bit more. I mean, let some more insight into what's happening. Okay, so I'm not writing much on the board because it's more of a story building on and showing analogies, right? So let's understand this from a different perspective. So we look at classical gradient descent. When we looked at Lipschitz continuity, we said that the function, the overall function, now I'm looking at the overall function as sum over all the function evaluated at each of the individual data points, right? So the norm is also basically norm of the summation. So this expression in blue is a norm square of summation. So norm square of summation is what we kind of assume so far will be upper bounded by the Lipschitz continuity square. On the other hand, stochastic gradient descent, what are we going to do? We are going to take the norm square of summation, but then sample a point at random and assume that that point is representative of all the points in average, right? So the difference, of course, is because I'm sampling a point at random, I'm not really computing the norm of the sum. Cumulatively, as I keep sampling points, I will be looking at the norms of individually sampled points, the gradient of the individually sampled points. So it is basically dealing with the summation of norms, right? So you may ask, what is the connection between the B of the gradient descent and the B of the stochastic gradient descent? What's the connection between these two? What do you think, right? What do you know from Cauchy Schwarz? What do you know? Jensen's inequality, yeah, I mean, basically, a convex combination of points is another view of it, right? We are looking at the gradient. In machine learning, it's a convex combination of the individual point gradients. Think of this 1 upon n as being drawn inside. You can take the 1 upon n inside. It's a convex combination of gradients. So, I mean, you can just use convexity. The function is convex. So what do I know? I know that 1 upon n times the sum of the gradients, which is nothing but a convex combination of the gradients. What's the relationship between convex combination of the gradients and norm of gradient? So convex combination of function values and function of convex combination. What do you know the difference? Yes, right? So that's the inequality we get here. So the blue should be less than equal to the yellow. Right? This is just simple convexity, right? If I have alpha W1 plus 1 minus alpha W2, its square is less than equal to alpha naught W1 square plus 1 minus alpha naught W2 square. Which one? Oh yeah, sorry, this yellow term, this there's a discrepancy. Okay, I'll correct that. Let me do that right away. Good point. I just copy this. I'll correct it in the later. Thanks for bringing this up. Yeah, thanks. Looking correct now? Yeah. Right. So what are we saying? Because norm is also convex function, by the way. Function is convex is one thing, but norm is convex function. So norm of the convex combination of the points. Now think of this as convex combination of points. Norm of the convex combination of points will be less than equal to the convex combination of the norms. Right? So basically this gives you a feel that the gradient descent based Lipschitz Lipschitz continuity factor B square of the gradient descent Lipschitz continuity factor should be less than equal to the square of the Lipschitz continuity factor associated with stochastic gradient descent. Okay. Now this basically is saying that stochastic gradient descent is now loosening things a bit. The stochasticity is certainly loosening things a bit. So it's not that everything is status quo. Things are changing, which is also making sense, right? I mean, if possible, you should just go for the full gradient descent. But the problem is there's a lot of redundancy. That's what we discussed in the last class. And at times you can't even just compute the gradient on all the points with large language models. That's certainly a problem. In fact, when you pre-train a foundational model, you don't even visit a point more than once. At best, you may do 2 epochs, right? So how are you going to compute a gradient across all points? It's infeasible. So which means we are compromising on the B. There's a bit more liberal Lipschitz continuity constant, as I've written there in text. However, this also gives you some motivation. Oh, if there is a possibility. So let me write down this important point, right? So what have we observed? The stochasticity, the pro, and the cons of stochasticity. So the pro is, of course, n times faster epoch, right? But the con is approximate gradient, but there's also upper bounded, loosely upper bound B. The pro, of course, is its feasibility. Feasibility in large training, especially large language models. So this is feasible. You can't even do non-stochastic otherwise. So, but the question is still, can I bridge the gap? So this slide gives you some motivation for bridging the gap. Okay, so it turns out that you can bridge the gap if you. So if imagine that instead of I taking the norm completely inside, if I were to group some of the gradients, I'll create groups. Then do you think that I can get some intermediate point between these two inequalities? Right? What are we saying? Well, this mini batches. So mini batches could bridge. We will come back to mini batches soon, but for now, let's just motivate mini batches using this very important expression. So between these two, I'm putting one more, which is similar to the first one in the sense that there will be a summation outside. Similar to the second one, that there will also be, there will be a summation inside. And like the second one, there will also be a summation outside. So there will be two summations. Okay, so what will be the summation inside? Like the first one, I'm going to do summation over all i's in a group. Okay, and I can just consider, well, 1 upon n, sorry, 1 upon, this was 1 upon n. We'll do the normalization later on. And like the second one, I will do a summation outside over all the groups. So as you would expect, I mean, you should expect that this inequality wise also is going to be standing between the two. This is a motivation for mini batches. One motivation, many more. So you'll see how many points you can accommodate in your memory. That's what happens with large language modeling, right? The GPU memory becomes your constraint. The GPU can accommodate all the points, one thing, but obviously you can't. This is well 64 GB, 128 GB. See how large the band, 1000, 2000K, whatever, right? You can accommodate. And certainly that theory shows that can lead to better convergence. Yeah, tabulating the comparisons. So if we look at subgradient method with convexity, which we did already, 1 upon square root t. What we didn't talk about was subgradient with strong convexity, which will give you 1 upon t. We didn't talk about this. Now, our interest is not just the table on the top, but comparing it with what happens with subgradient. So moment you bring in subgradient, it turns out that, well, with convexity, you have 1 upon t when you do full. When you do stochastic, you get 1 upon square root t, right? In fact, with subgradient also, sorry, even with gradient, you get 1 upon t, 1 upon square root t. With subgradient, the stochastic basically is 1 upon square root t, and the full is also 1 upon square root t. Okay, so what this table is telling you is that the gain you get, or in some sense, there are hidden costs associated with subgradient. There are hidden costs associated with subgradient. Because of that, whether you do full or stochastic, you are 1 upon square root t. Whereas if you consider gradient, you can see the gap more explicitly, that there is actually a drop when you go to stochastic. Right? So because earlier we did only the subgradient analysis. This we didn't talk about, I didn't present any results, but there still seems to be a significant gap. And the gap is even more significant, right? Not for subgradient, but for gradient when you consider strong convexity. So for subgradient strong convex, 1 upon t, 1 upon t, we saw that earlier, the two results I showed you. But when you consider the gradient strongly convex, we already saw it's, I mean, basically constant number of steps are required for every 0.1 drop in epsilon, right? Whereas that basically results in order of 1 upon u minus L raised to t, exponential, right? But in the case of stochastic, it's 1 upon t. I mean, it's almost like subgradient. In fact, the behaviors for stochastic is not changing across gradient and subgradient, which is also not surprising, right? Because subgradient was kind of considering a lower bound hyperplane, right? Lower bounding hyperplane for the function. Now that lower bounding could have come and it was existential, if you remember. Subgradient processing, there's a subdifferential class from which you pick one. There's a similar flavor, right? In subgradient, you're picking one from a large set. In case of stochastic gradient, also you're picking one from a large set. I'm not saying they're comparable in practice, but in theory, there seems to be some parallel, right? These are similar. Okay, so I'll just, yeah, please.
Strongly convex with Lipschitz smoothness. So we are saying that we are manifesting Lipschitz smoothness like this.
So this was not Lipschitz smoothness, right? For the gradient. Lipschitz smoothness. This was a Lipschitz smoothness. Yeah, you're right. In the presence of the gradient, you see the gap. With subgradient, you don't see the gap. That was the smoothness and strong convexity. Smoothness. Actually, this also is with smoothness. 1 upon T is also with smoothness. Stochastic is also with smoothness. I mean, the goal was to highlight the gap. We're not being very elaborate here. So this is when you get, when you additionally assume smoothness. And so the point is there's something amiss. So while I said there is one motivation which was brought out even in the case of subgradient approaches, the gap with respect to the Lipschitz continuity factor, right? This was one motivation. So motivation one for mini batches, but there seems to be more motivation. So the motivation two we'll just call it mini batch, okay? It's called MB often. Motivation two for mini batch is gap gap in case of gradients. Gradient descent between full and stochastic. This is the second motivation. Why? Well, if I were to consider now, instead of individual points, if I consider larger graph, let's imagine the full data split into 3 parts or 2 parts. Obviously, I would expect the behavior to be similar to the full case, right? But if I have to split the data set into as many as the number of points, obviously I've got the stochastic. But if I group the stochastic points into buckets of 2, 3, 4, I would expect behavior tending towards full. So more I can have the size of the batch, mini batch, the more number of points I can accommodate, more I would expect behavior tending to the full case. Is this clear? Yeah. True. Yeah, for stochastic, can we guarantee descent? No. Very much like subgradient. See, subgradient also you sample, stochastic also you sample. No. No guarantee descent. But now, hopefully, you see why there are so much scope in this space, right? There's a lot of contribution that engineering can bring in. If you knew the nature of the function, you could also bring a lot more analysis, right? So there's a big space, wide open space. So optimization is super critical. Let's not assume that optimization is solved ever. Okay, so this is mini batch. I think we have given enough motivation for mini batch stochastic gradient descent. Instead of taking instances, use a batch of them and take the average. Right? Extreme cases are, of course, a stochastic gradient descent case where M is 1, which means each batch has size 1, and M equals N is full gradient descent. So with that, I will complete what I wrote on the board here, right? So what will I do here? I'll be considering are 1 upon m inside, because each batch, the size of each group is m. And there, of course, outside we'll have outside here. 1 upon the number of groups. No. We just call it, m n divided by m. N divided by, or you want to put it better, you just say m upon n outside. Is this clear? Yeah. Sorry?
Can we do that instead of that and get the equation of that?
And yeah. So we can do all kinds of momentum improvisations on across batches. Yes. So your earlier question was, can we eliminate points which are not aligned with the gradient? Now you have a defined question whether we can compose batches more intelligently. Should batches have diversity? Should batches all be aligned with each other? That's also a question, right? One advantage of having batches aligned with each other would be that you're adding signal, right? You're basically adding signal. But if you just take batches with two diverse points, they may just cancel out each other, right? So, but there's also, I mean, if it all depends on your batch size. If your batch is big, obviously diversity will also help. So yeah, all these are very valid considerations when you compose batches. Any other questions? This is very interesting, right? Variance. So variance of the gradient estimate is 1 upon m of that of vanilla stochastic gradient. This is important, right? So what is happening here is the variance when you consider with a stochastic estimate g t tilde. Sorry, this is the complete estimate. This is a complete estimate on the left hand side. Now this variance is 1 upon m times that of the variance that you'll get through stochastic vanilla stochastic gradient descent, right? So this is a useful thing. Right? M, for example, if m is 1, what will happen? Let's take the extreme example. Each group has size exactly 1. So the variances will be the same. Because groups have size 1. Moment group has size 2, the variance with respect to your mini batch estimate, which is G tilde T. G tilde T is the average across those mini batches. That will be 1 upon m times that you would have had using a vanilla stochastic gradient descent, stochastic descent. Okay, so there are a lot of there's a lot of literature on variance control, variance adjusted, right? The variance, of course, with stochastic gradient descent is a big concern. And so that's a third perspective. I listed 2. There's a third perspective behind mini batch, which is motivation 3. Okay, summarily variance with mini batches 1 upon m times the variance of stochastic gradient descent. And that possibly is also explicit in this inequality, but we're just writing it out separately. Okay, so going back, how would you modify a stochastic gradient descent to bring in mini batches? Where will you make the changes? Sampling I uniformly at random. You may want to make a change here. Would you sample k elements, or would you create? So the other perspective is So one perspective, as he's pointing out, is sample k points into a mini batch. The other is I'll create those mini batches beforehand. I'll sample a mini batch. So should these mini batches be dynamically composed or should they be statically composed? It's also a consideration, right? I mean, many of these inequalities we are with writing with the assumption that these mini batches are static, right? So yeah, mini batches bring stability by sampling a batch. So one way is I say I'll create those batches beforehand. At least will make the job of sampling easier. See, that's the third perspective. You don't have to sample from all the points, especially if you want to consider sampling without replacement. I mean, sampling without replacement is very difficult in practice, right? Who is going to keep track? But if you want to consider in some weird case, bookkeeping is easier with mini batches. So instead of iteration being n times cheaper, what will happen? Each iteration you will now consider a mini batch. So it will be how many times cheaper? N by. Now this will be changing to n divided by m, right? Yeah, the unbiasedness in the gradient estimate will still remain. That is still critical. Okay, so I think many points we have already written, but it is a little bit of repetition here. So the stochastic gradient descent or batch stochastic gradient descent, some of the negatives, right? Slower convergence compared to gradient descent. Overall, right? It will be slower convergence because we have got a looser upper bound on the and we saw there is a gap already associated with gradient approaches, right? When you have gradient instead of subgradient, then there's actually a gap as well. So it is slower. We have enough evidence that it is slower, right? And though we keep saying that gradient unbiased, it is after all noisy. That's why variance reduction happens through mini batches. But still, there is variance. Mini batches still more variance than the full gradient descent, and not guaranteed to reduce at each objective. So at each iteration, the objective is not guaranteed to reduce. And finally, now we get into learning rate problems. Learning rate becomes even more challenging. In fact, that's the motivation for the next part of our presentation. We want to do something more intelligent with learning rates, especially given we are stochastic. Learning rate is going to become trickier, right? So you need to give some thought, right? Despite all of these cons, why ML researchers prefer stochastic gradient descent, right? So there are some pros. We are going to list some pros here. And by the way, descent itself is a misnomer, right? So, well, pros from a machine learning perspective, is it possible that they help you get out of a local minimum? Maybe some points are pathological points. Instead of considering all the points, if I consider the good points which are not pathological, maybe they help me get out of a local minimum, right? Or there's another perspective. Maybe I pick up an adversarial point, right? So if I had to classify, right, I mean the wall color here, right? So the color of the wall, if I were to take some of these points which are having these grills, the brown pixels, I might mistakenly think that the wall is blue, wall is brown, right? So of course, informed point selection is important. But if I want to distinguish between the wall and so this is also blue, the floor is also blue, the wall is also blue, and for the time being, assume that both are the same blue. The shades are different, but let's assume they are the same shade of blue. Now I want to kind of pick a point adversarially to determine which is the wall, which is the floor. So blue is not going to be sufficient, right? I'll pick something which will distinguish the wall from the floor. What is it? What distinguishes? Huh? Yeah, those grills on the wall. Certainly. So those grills, while wall classification may not benefit from the grills directly, If you want to distinguish the wall from the floor, they serve as adversarial points. You understand? So there is a value in being stochastic then. Right? So of course, there are other things like per iteration cost being cheaper, and initial. So that's another point, because points are often quite redundant. Like if I had to classify the floor and imagine every pixel was a different point, all these points are taking all the points is total redundancy, right? And if I wanted a classifier to converge quickly, I just pick some random sample from the floor and I'm done, right? So at least initial convergence becomes faster. And of course, with mini batch variants, you also get better accuracy. And especially if the data set is massive, mini batches certainly help get you better accuracy. And by the way, all this is even for non-deep machine learning. There's a very nice ICLR 2020 paper, which is called Identity Crisis, Memorization and Generalization under Extreme Overparameterization. So, and that makes a case for stochasticity, right? But it also kind of draws cautions. So it says there are problems, Baynes also, with just being overly stochastic. Right? If you're too stochastic, your attempt is to generalize, but in that process you will generalize. See, I mean, a very naive classifier which says everything, a classifier which is say a constant, right? Constant is a naive classifier. What you look, A transpose X plus B is still naive. A square, X square A plus bx plus c gets more complex. So being naive can also lead to generalization, right? On the other hand, if you have too many points in your mini batch, consider every point is a gradient, then you may land up memorizing. There's a trade-off between memorization, memorizing the entire data set, versus generalizing beyond that data set. So do have a look at it. Okay, so the more key important point takeaway from all of this is generalization is certainly important. So therefore, stochasticity is of value. I mean, memorization is a concern, but you want your models to generalize. That will also help ensure that you're efficiently I mean, you want to be efficient and generalize, right? Stochasticity gives you that. And sometimes we find that techniques which perform better on training set suddenly are bombing on the test set. So stochasticity also guards against such cases. So it generalizes very well. Of course, there's still a large gap between the theory of stochastic gradient and empirical performance. So that's still a big problem. Okay, I think there are plenty of research topics and maybe PhDs here. Most of the analysis, as you saw, is basically through expected function converging to true value. So of course, you should also look at regret bounds in online learning. I won't be doing that, but that's since we said we'll move away from too much of analysis. But Professor Vivek Borkar does a lot of regret bound analysis. And though, what is the notion of regret bound? What do you understand from the word regret? Could have done better, right? So students who are not there in the class today, right, could have done better had they turned up in the class. So it's a good message you can send them. So if they have a problem they're not able to face in the end sem, they can regret, right? So the model can regret that it did not pick certain data points. So when you quantify that regret, what is the gap between the performance when it had it picked the point as against I did not pick the point? So that's where the regret bounds come in. And the learning rate is still a big nightmare, right? So we'll come to the learning rate. Okay. Now probably the last slide before I move to the learning rate tuning itself. The learning rate tuning is not at all trivial. Complex rules exist. I mean, many of them based on empirical observations. For example, when the learning rate is too large, the gradient descent can inadvertently increase rather than decrease the training error. because we're not dealing with descent anymore, right? So the descent is not a descent direction. So learning rate large becomes even more suicidal, right? Because you have just one point or maybe a mini batch which is trying to represent the entire collection of points. So when the learning rate is too small, training is not only slower, that is another problem, right? Um, so the whole goal was stochastic was to move faster. But if your learning rate is small, then you're not moving fast because of the learning rate, despite being stochastic. So um, the question is, if you had a limited time, right, what would you optimize? Would you optimize any one hyperparameter? And let's say there's stochastic gradient descent. The only hyperparameter is the learning rate. Even more so, as I said, with stochastic methods. Already learning rate is giving us sleepless nights for several classes now. He'll give you more sleepless nights with stochasticity. Okay, so learn to remain awake through nights because of stochasticity. Right? Of course, the same tricks. If you can always tune it on validation set, that still remains. But we look at slightly more sophisticated decay rules, etc. Somebody had a question. So there is one. Now the schedules are going to become important. How are these learning rates going to change? There's something called linear schedule, but there is also cyclic schedule. So instead of saying just they keep on decreasing, there will be some cyclicity in the learning rates. Why? Because there's also cyclists. You're cycling through data points, right? That's an important point to note. That because you're cycling through data points, the learning rate may also need to cycle. ah, so this is going to be an important point. The way learning rates are changing. Okay, so we want to improve the convergence of stochastic gradient descent. Yes, better low complexity per iteration, but slower convergence. What can we do? So we list down points that really bother us here. What are the points? So deriving a principle for reducing variance. How can learning rate help me reduce variance? One is of course mini batch, which we already talked about to reduce variance. So can there be learning rate schedules that can reduce variance? Can we bring in, of course, acceleration momentum? That is a no-brainer. But can acceleration and momentum be brought in a way that is more faithful to stochasticity? See, we don't want, we'll look at blind adaptation. One is blindly adapt, nested of or heavy ball, the two variants, right? And can we also do some subset selection? That's another very important point. The same point you mentioned, right? How do you compose the mini batches? Of course, engineering can come in there. If I know the nature of the data set, nature of the documents, I'll may say, well, there's a curriculum. This is how you should ideally try and compose. At least in the beginning, see, like a child, the child learns to walk. You want to make sure that you reinforce the learnings quickly, right? So you may want to give similar kind of mini batches in the beginning, so that the model learns and is not confused. But as the model learns, let's say the model has already, let's say pre-training a large language model, you've already exhausted the cleaner documents. Then you may want to play a little adversarial, right? You may, even this wall versus floor discrimination, you would play adversarial only when the model has already learned some features. First let it mug up the fact that the floor is blue and the wall is blue, and then you bring in the distinction, right? So at which stage you learn. So in fact, Pratik Chanda, we submitted a paper this year to AAA. It was exactly this. The subset selection should also depend on which stage of the model the subset selection is being invoked at. So you may initially look for representation functions, and once a model has learned, go for diversity, right? In the samples, the mini batches. Hmm.
Happen from the same class in one batch, he said, and later you diversify that.
Right. But can that learning, the fact that initially the points should be from similar classes, later on from different classes, can that learning be a little bit more driven by math? We will talk about it later. This representation means, I want points which represent this set, right? Diversity, like the wall. representation of the wall is largely based on the blue pixels, but diversity will also include some of the brown pixels here. Right? So one step towards this, you say, oh, Minibatch is fine, all of this is fine. Can I make a small delta step? And we should always think in terms of small delta steps. So what is it here? Stochastic average gradient. So a natural step is, a natural thought process is, well, what if I keep storing, right? Why should I just compute mini batches, compute the gradients and throw them away? So what do we do here? So WT plus 1 is WT minus what we do, right? The stochastic average. But there's a slight catch here. GTI is the gradient if I equals IT. It's in a lookup. If it is not there in a lookup, right? If it's not there in the index collection, so if it's not there in your randomly sampled collection, then you take it from the previous iterate. So what are we doing here? We are saying, well, I'll do random sampling, composing, whatever, mini batches. There's no mini batch here, it's just still stochastic gradient, but you can do mini batches as well. So let's keep mini batches aside, just sampling a point. Now, if that point, if while computing gradient, if that point has been selected currently, I look at the latest gradient. If it is not selected, I look at the previous gradient. You may say this is good, right? Because this is getting you towards a full update. The only thing is I'm making change only for that one point based on the current iterate. All others remain from the previous iterate. Is it clear? So let me provide a little bit more insight here, right? So what are we doing here? You're storing the gradients, and this is cumulative. Okay. So all the previous gradients I'm storing. Only I'll update the gradient that the gradient for the point that has been picked randomly. Rest will remain the same old gradient. And so as I'm showing here, right? This is basically what does this amount to? It's saying is WT plus 1 is WT minus update for that point minus a constant. So rest is all constant. Why? Because they are coming from the previous iterate. I've just rewritten the same thing slightly differently. So this is the non-stale update. The green is the non-stale. The blue is a bunch of stale updates. So the problem, of course, is storage. Who's going to? I mean, now we have put the entire onus on some large cache. I have to retrieve from the cache, basically, and keep the summation update. So updating the summation and then storing it back is going to be a little bit challenging. So there are a lot of engineering tricks. Engineering is super critical here, right? You're dealing with matrices, dealing with dot products. So if you can somehow avoid storing gradients and only look at the dot product, storing the dot product. And the gradient is a long vector. If I have to store all the previous gradients, it's going to be challenging. But now, if I had to look at the, so there's also a parameter vector, right? What we are talking about is gradient with respect to individual points. But there is also parameter vector. Now, if I'm involving storing many previous many previous points updates, right? I'll have to probably store also those parameters, or at least a dot product of those parameters with the current gradient. And the moment the parameters are updated, I will also update the dot product. So a lot of engineering gimmick is required here, right? It's not easy. It's easier said than done. But it's good. I mean, it looks like, okay, it's trying to get the best of both worlds, right? This was by Bach in 2012. So if you look at its performance, right now, none of Bach's paper will, or every paper of Bach will have some analysis, mathematical analysis. That's the strength. So what was shown there? Well, if you go for the stochastic average gradient or the hybrid version, then you're starting to tend to become what strong convexity gave you, which is good, right? Because if you remember, stochastic strong convexity was just 1 upon T. in some sense that gap is being bridged now. Of course, there's a lot of constant factors here involved in this exponent, the base of the exponent, but it is still, at least 1 upon t, right? So it's looking better. And the speed up, they also show it's applicable in practice, modulo all the engineering tricks, and still a lot of memory. No matter what you do, memory requirement will go. That's a given. So there are many other approaches, right? And you can feel free to add to this list. If there's any semblance of any of this with your seminar or your project, please do add to this list. So these are all, as I said, potentially relevant to one or more of your projects. They will be, right? They will be. Because stochasticity is going to be in your DNA. So there will be a whole bunch of other papers which have showed similar kind of things. So for stochastic variance reduced gradient, proximal SVRG, hybrid of SVRG and SAG, and so on, right? But at the similar spirit. So how does it perform, right? The hybrid thing. So I'll just I'll talk about the LBFGS a little later today, hopefully. But specifically, if you compare just the SAG, LS, and is stochastic gradient and this average thing, you can see that it is going down much faster, right? Modulo the memory requirement. Okay, which is what was expected. So each update is very small. Update is just one. Lot of memory updates, of course, will be required. And as a result, so you can see that full is always helpful. But is it practical? Is the memory utilization here warranted? I think these are questions to be answered. Now we look at some more variants, so which are a little too stochastic. So the hybrid was not so stochastic, but we'll look at more stochastic variants. The theoretical convergence results will not apply if you are dealing with non-convex. But every such paper will also have, okay, if the function is convex, how does it converge? That's a default, right? So you have to learn the tricks of how to show 1 upon t, 1 upon t square, raised to t, right? What does the base look like? So, I mean, convexity is a given. You have to use that as a tool to study how good your algorithm is. And you see, most of the time, there's in theory and practice, there is some connection, some resonance. Okay, so, right. So now vanilla stochastic gradient descent, momentum variance is that we have done. So momentum variant descent and adaptive methods. These are what we will look at next. Okay, and when we say adaptive, these adaptive methods are going to look at adapting learning rates. So these are the ones that are very, very commonly used. So one last note before I move there. There's a hidden advantage of convex analysis, which I already said multiple times, but I'm re-emphasizing here. The gaps, we saw gaps, we bridged those gaps using adaptive methods. That's one advantage. We then, when we bridge those gaps, we also see, some lower bounds continue. That often also results in your effort to bring in adaptivity, learning on the learning rates. And also, for example, the analysis we did with Lipschitz continuity also gave us motivation for mini batches, right? If we do mini batches, how does it perform? And so on. And then, of course, the gap between gradient and subgradient methods also starts emerging, right? And again, we found that there was a gap in gradient, not in subgradient, because of the sampling in subgradient, which is similar to stochastic. But with hybrid, we are able to reduce the gap significantly. So all this is thanks to convexity. So never undermine the importance of convexity. So now momentum, right? We'll start off. I'm going to give you some food for thought for homework. So what is the first step? How will you bring in momentum to this very naive stochastic approach, which is based on approximating the gradient with a simple point? So earlier we were using GT, but as I said, GT is nothing but some I index. So since we have to be more specific, I put an I index here. So what's the update? What will you do to bring in momentum? You'll have to have a vector v and decide whether to use a vector v also within the gradient, right? So we'll give a generalized flavor and hope you can connect to the generalization. So what we'll do is um, we'll have alpha t, but alpha t applied to f with what you see here as velocity, right? Gamma t times wt minus 1. And the velocity, this is the velocity, wt minus 1 is the velocity. But I have used the beta t multiplicand because, as I said, now learning rates are going to be important. So give a little bit more attention to alpha, beta, gamma, etc. Right? So there's a there is a multiplicand, the beta t with the velocity component. Inside the gradient, there's a multiplicand gamma t with the velocity component again. And then there's an alpha t sitting outside the gradient. This is like a learning rate, right? So does it give us both heavy ball, that is Polyak's, as well as Nesterov accelerated? And it turns out yes, right? So if you set gamma t to 0, then what will happen? This entire thing will vanish, right? And this bracket will just move here, right? This makes sense? This is what will happen if gamma t is set to 0. That's Polyak. On the other hand, if I set gamma t to be beta t, or just, up beta t here, then you get Nesterov momentum. Is this clear? So we can recover both from this very generalized expression. And since you're going to get a little bit more complex with these learning rates, good to have a compact representation. Okay, so this is what we are doing. I hope the connection is clear. We'll have a gamma t inside, a beta t outside in the velocity component, and an alpha t overall, the learning rate. And as I pointed out, heavy ball momentum will have gamma t 0, and Nesterov accelerated gradient will have gamma t set to beta t. Okay. With that, now what can we do further? So the problem, as I said, is these are not adaptive. This is the learning rates are not adaptive. Sorry. The direction is being adapted with respect to momentum. Learning rates are not adaptive, right? Adapting to the behavior of the GTs. Can the gammas and the betas and the alphas also adapt to GTs? That's the question. And without the right learning rate, the convergence can be slow. It's a big problem. Learning rate is a big problem. So there's a nice fix. And the nice fix is actually inspired by second order methods. It's inspired by Newton's method. So I will just quickly talk about Newton's method and then leave food for thought, right? So what does Newton's method say? Well, instead of gradient descent, which was based on a first order approximation of the function, do an update based on the second order approximation of the function. And good thing about Newton's method is you get a very good learning rate there. Complex direction, the direction for descent is very complex there, but the learning rate is very nice. Okay, that's where we're going to get inspired by Newton's, right? So I'm going to take a small detour, right, which says, okay, why Newton's rate? Because you're looking at Taylor series approximation of the function. The gradient descent was based on first order approximation. We'll turn to Newton's, which looked at the second order approximation, and take inspiration from there. Okay. And Newton's method actually looks at what we call the Hessian matrix. Okay, so let's just take a small detour and then we'll conclude for today. This is a very simple approach. And in fact, it gave rise to many other approaches, quasi-Newton approaches, In the plot, there was this LVFGS. That's a quasi-Newton approach. It's inspired by Newton's approach. And that will also uh, lead to better appreciation of matrices, which are used extensively in these adaptive learning rate based approaches. Okay. So I'm going to just okay. So this is covered in the sections 4.5.2 and 4.5 to 4.5.6 of the notes that I have online. In fact, this is on Moodle. So this is the section. Newton's method is explained in that section. Okay. So what is it? Oh, sorry. Okay, so think of this Newton's method as a steepest descent algorithm. What did gradient descent do? Gradient descent said, I will consider the first order approximation f of x is f of xk plus gradient at xk of transpose of the gradient xk times x minus xk, right? This part was ignored. Now Newton's algorithm says, let me look at the second order approximation and try to minimize it. Right? The other way of looking at Newton's approach is I will try and find that descent direction which gives me the best or lowest dot product with the function, but with its norm based on the Hessian. So what is it saying? Argmin, minimize, give me the direction delta. This is another equivalent way of looking at it. Give me the direction delta k that minimizes the dot product of the function with that v, vector v, and such that the matrix induced norm of v based on the Hessian matrix at that point is 1. Right? If this were replaced with a gradient, so what happens? Okay, if instead of this Hessian based norm of v, if I consider the gradient based, the L2 norm of v, then what will I get? The answer slipped from my tongue already. Gradient, right? The gradient direction is that which minimizes this dot product under the constraint that the direction is having L2 norm of 1. If we change the L2 norm to the Hessian induced norm, then you get the same thing called the Newton update. Okay, so both of these are the same. So now let's look at the second one, which is much easier, right? If I had to minimize this function, the quadratic approximation, what would be my descent direction? I mean, what would be my solution? You can come up with a closed form solution. All of you know. We've done this, right? How do you come up with its closed form solution? Differentiate, set the gradient to 0. Gradient with respect to x. Xk is already fixed because I've what have I done, right? What have I done here? I've taken a point xk. Okay, this was my function f. I took a point xk here and came up with a quadratic approximation along. This is a quadratic approximation q. Right? This is a function of x with respect to xk. So what happens if I set this gradient to 0? What will I get? Gradient with respect to x. You'll get, yes, you should get fxk from here plus, or is it minus plus? is what? Sorry? X1 is xk times right. So if you set this to 0, I'll just give you a few moments, couple of minutes. If you set this to 0, then what do you get? X to be is xk. Just take this to the other side, right? It's what? Minus xk minus the Hessian inverse of the Hessian times the gradient. So xk plus 1. So that's what I've written. You can think of this as xk plus 1. Xk plus 1 is xk minus Hessian inverse at k times the gradient at k. There's no learning rate, fortunately, right? There's just directly. So this is the so-called Newton update. There's no learning rate involved here. And in fact, what is happening is basically you're capturing curvature. And what you will do is you will stop till your lambda square. So what is a lambda square? It's documented in the notes very clearly. You can go through the notes. Oh, where do I go? So this lambda is basically, this lambda square is helping you measure the square of the descent step. So it's basically saying if lambda square, which is the squared norm, the Hessian induced norm, the Hessian induced norm of the descent step, if it is less than some epsilon, then stop. Which means, so that's what we do in gradient descent also, right? If your norm of the gradient or the descent direction is very small, then stop, right? It's basically 0. The difference here is I'm looking at lambda, which is the norm under the Hessian of the descent step. Okay, then that turns out to be this quadratic expression, gradient transpose times Hessian inverse into gradient. Right. No, not direct. Yeah. Other than the fact that that's also looking at second order. There's no connection. Yeah, so let's not confuse. We'll look at only this independent of that, right? So this is this is it. So this is the, now the algorithms, we'll stop now. The algorithms we'll discuss next class will be all be inspired by the curvature being captured to the Hessian. The challenge, of course, is Hessian computation. This is a massive matrix to compute, right? The Hessian at every step. So, invert it also, right? So what the variants of, very good point, right? Inverting the Hessian, instead of that, if I could approximate the inverse of the Hessian. That's what many of these quasi-Newton methods do. They say, oh, I will keep track of, I'll do some bookkeeping of what the inverse of the Hessian would have looked like. It'll start with some identity matrix, right? And then the quasi-Newton methods, what they do, they'll compute a bk plus 1 based on a bk, which is an approximation to the inverse of the Hessian. Right? This is important to approximate the inverse, not the Hessian itself. Who cares what the Hessian was, as long as I can approximate it inverse properly? And that they try to do using some very efficient. So it's there in the BFGS, is there in my notes. I won't get into BFGFs. What we'll do is we will directly use this notion of a matrix which captures curvature. Keep updating the matrix. That's what Adam will do. That's what many of these variants will do. So I think the homework problem, I gave already 2 homework problems. The third homework problem is think a little bit about how we could actually get this curvature information through this Hessian approximation. Okay. I will meet on Thursday. Very good question. I think please continue asking these questions. It really helps motivate. Thank you.